Hello students, Dr. DS over here. Let's solve some few questions on solubility. These are some kind of questions you can be asked in your exam. Okay, so exactly 0.113 milligram of silver bromide will dissolve in 1.0 liter of water. What is the value of the KSP for silver bromide? And we are given the molar mass. Okay, to calculate for solubility, for KSP, the solubility product, you need your solubility. And solubility is just concentration at a particular temperature. This concentration or your solubility can be expressed either in mole per liter or in gram per liter. This is molarity. This is mass concentration. But when you are calculating for KSP, you have to use this. You have to use your concentration in mole per liter, not mass concentration. So we're given the mass of the compound, then we're given the volume. So when we divide mass by volume, we are going to get density. That is our mass concentration. So first, let's get our mass concentration. Then we can proceed and get our molarity. We know the relationship between mass concentration and molarity. Rho equals MC. Molar mass times molarity will give you the mass concentration. So we can get the mass concentration of the silver bromide to be equal to the mass 0.113 milligrams. Remember um we did prefixes, so milli is 10 to the power minus 3 over the volume we're given 1.00 liters. We are basically going to get 0.113 by 10 to the power minus 3 gram per liter. Now we have to convert this to molarity. So rho equals MC. Our C is rho over M. So we can get our molarity to be 0.113 by 10 to the power minus 3 all over the molar mass. The molar mass was given to us over here. So 187.77. Then we are going to get our concentration to be 0.018 by 10 to the power minus 7 mole per liter. Now we've gotten the concentration, which is like our solubility. Okay, now we have to write the equation of dissociation of the salt AgBr aqueous. You must bring the state. Without it is zero. Ag plus aqueous state is very important. All atoms are balanced. So our KSP, if the solubility is X, then the mole ratio of this to that is 1:1. Here is also 1:1. So X and X. So our KSP is equal to concentration of Ag plus raised to the power its stoichiometric coefficient. So the coefficient is just 1. So to the power 1. Multiplying concentration of the bromide ions to the power its coefficient here, which is also 1. So our KSP equals this concentration is X, this one too is X. So our KSP equals X squared. KSP equals the X is our solubility, which we calculated for 0.018 by 10 to the power negative 7 all squared. Then finally we get a KSP to be 3.622 by 10 to the power minus 13. Yeah, you can add the units. You must add the units because this is your molarity. It was in mole per liter and it was raised to the power 2. So you need to be what? Mole to the power 2, liter to the power negative 2. Next question. Write the value of the solubility product of the salt Pb3 PO4 subscript 2 in terms of H solubility S. So we are seeing the solubility of this salt is S. Let's write an expression or the value for the KSP. So we have to write our equation of dissociation of the salt Pb2 plus Here, Pb2 plus PO4 3 minus. This goes there, this comes there. When you are done, so you have to put it in aqueous medium. Bring the states. Without the states, it's wrong. Now, let's balance. Over here, we have PB, just one. Here, we have three of them. So we have to multiply here by 3. Remember when we did the redox? This is the frequency of the atom. This way you put the charge. And this way you put the mass number. This way you put the atomic number. Yeah, so the frequency here is very, very important when you're balancing. So if you have Br, the frequency is 1, 1 atom. Br2, frequency is 2, 2 atoms. So if you have Br and you put 2 here, when you're balancing, it means that 2 times 1 is 2. So 2 atoms here, 2 atoms here. So now we check here, the frequency is 3, here is 1. So I put 3 here, so 3 by 1 gives us 3. 3 atoms, 3 atoms. Here, this whole thing is standing as 1. The frequency is 2. So here to is standing as 1, the frequency is 1. So I have to multiply here 2 by 2. And everything is okay. Now let's see the KSP. So if the solubility is S, mole ratio here is 1 is to 3. Here the coefficient is just 1. 1 is to 3. So here is 3S. 1 is to 2. So here is 2S at equilibrium. Our KSP equals concentration of the Pb2 plus ions raised to the power its coefficient, which is 3, multiplying the concentration of the PO4 3 minus ions raised to the power its coefficient, which is 2. So now KSP equals concentration here is what? 3S raised to the power 3. Concentration of this is what? 2S raised to the power 2. KSP equals, here we get 27S cubed multiplying 4S squared. KSP equals 27 by 4. That gives us 108. Then applying lots of indices, we add the exponents. So S to the power 5. These are expression for the KSP. Now the B says that, so this for A. Given that the solubility S is this, calculate the KSP. So obviously we are just going to put it inside KSP equals 108 multiplying 1.5 by 10 to the power minus 7 to the power 5. Then finally, what do we get? We get 8.20 by 10 to the power minus 33 moles to the power 5 liters to the power negative 5. So we've calculated for the KSP. Next question. Calomel, whose chemical name is mercury 2 chloride, was once used in medicine as a laxative and diuretic. It has a KSP equal to 1.3 by 10 to the power minus 18. What is the solubility of mercury 2 chloride in grams per liter? Yeah, so you see, you can be asked to express the solubility in grams per liter as well. So now, since we know the KSP, we can use the KSP to find the solubility, which is in mole per liter, because we said that when we are calculating for KSP, the solubility we use is mole per liter. Once we get the mole per liter, then we can change it to a gram per liter, and we know the relationship to use, isn't it? Rho equals MC. So straightforward, we just write our equation of dissociation, then we move on. So we have our mercury 2 chloride, AgCl2, aqueous. We have Ag2 plus aqueous plus Cl minus aqueous. Frequency or balancing number of total number of atoms. 1, 1, here 2, here is 1. So we multiply here by 2. So once you get the solubility, if the solubility is x, 1 is to 1, so x, 1 is to 2, 2x. Now Ksp equals concentration of the Ag2 plus raised to the power its coefficient is 1, multiplying concentration of the Cl minus raised to the power its coefficient is 2. This concentration is here, x, multiplying this concentration is here, 2x squared. So Ksp equals 4s cubed. We have to find the solubility first. So cubic root of Ksp over 4. Our Ksp was given by 1.3 by 10 to the power minus 18. Then when we do this, we can get our solubility 6.88 by 10 to the power minus 7 mole per liter. So this is our solubility in mole per liter. I want it in what? In grams per liter, and we're giving molar mass. So we know that what rho equals mc. So in grams per liter, we just take our molar mass 472.086 and multiply by the concentration, which is the solubility in mole per liter, 6.88 by 10 to the power minus 7. We are going to get 3.25 by 10 to the power minus 4 gram per liter. This is our final answer. Next question will be done shortly. Compare the solubility of silver chloride in water and in 0.01 molar HCl. What is your conclusion? Ksp of silver chloride was given. So this is common ion effect, isn't it? Common ion effect. AgCl contains chloride ion. HCl also contains chloride ion, isn't it? And we said that common ion effect decreases solubility. Common ion effect and then complex ion formation, they decrease what solubility. pH can also affect solubility. It depends on the salt. pH can either increase or decrease solubility. And all these guys, they use what we call Le Chatelier's principle. So let's move on. So let's find the solution of AgCl in water. We put AgCl in water, and we are going to basically get Ag plus Cl minus all aqueous. Remember to bring your states. Aqueous, bring the aqueous. 1:1, 1:1 is already balanced. So if the solubility is x, so 1:1, 1:1. Ksp equals concentration of Ag plus multiplying concentration of Cl minus. Bring the expression, bring this. Raise to the power, its coefficient is 1, 1. So bring it. This step will be marked. Marks will be awarded for this step. So x, so we are going to get Ksp to be x squared. And we know the Ksp, so we can find the x to be square root of the Ksp. So root of 1.8 by 10 to the power minus 10. We are going to get 1.34 by 10 to the power minus 5. This is in water. Now I want to calculate the solubility in what? 0.01 molar HCl. HCl, we know is a strong acid. So we put it in aqueous medium to dissociate completely to give us H plus aqueous and Cl minus aqueous. It's balanced, isn't it? The equation is balanced. Yeah. So since it's balanced, it will dissociate completely. So whatever concentration you have here, whatever concentration of the HCl you have the same amount of what concentration of what H plus and concentration of what Cl minus. You see, this is a monoprotic acid. So assuming it was H2SO4 and you're writing it, you're balancing it. You'd have gotten H plus SO4 2 minus. But if you balance the equation, here would have become what 2 moles of H plus. So if here was 0.01, here becomes twice of that 0.01. You are applying the mole ratio 1:2, 1:1, then here has to be 0.01. But this is not the case. I'm just reminding you of something we did earlier in acid, base, and salt pH calculations. Alright, so back to the question. So we know that HCl in HCl we already have 0.001 molar Cl minus ions already. Then we are now coming to add this guy to this solution. So when we add the silver chloride, we put it in the HCl. This is what will happen. let's take the solubility to be x. All right, 1 is to 1 is to 1. So here will become x. Here will become x, but plus the concentration that was HCl, the concentration of Cl minus ions that will come from what HCl, so 0.01. Because before you added the silver chloride, there was already an initial concentration of Cl minus. So if you add this, the amount that what this guy will bring is the X, so plus the concentration that was already there. So now your KSP expression becomes concentration of Ag plus concentration of Cl minus. It becomes X multiplies X plus 0.01. So here there is an assumption. The assumption is that x plus 0.01 is approximately equal to what? 0.01. This is the assumption. Just like how we're doing calculations for weak acids, weak bases, the pH. And then we said that what? The acid dissociation constant Ka equals x squared over C minus x. And we assume that C minus x is approximately equal to C, and that K was equal to x squared over C, and S was equal to square root of KAC. So that is the kind of assumption we are doing over here. But here you should be careful. When you are done, you have to check the percentage dissociation, remember. And if it's more than 5%, you have to go back and do this and ignore the assumption. So to always be on the safer side, convert this to quadratic and solve. Get one negative answer, one positive answer. You choose a positive concentration. All right. So now let's see. We are back here. So if you make this assumption, then our KSP is equal to 0.01x. You see, so our x is what? KSP over 0.01. KSP was 1.8 by 10 to the power minus 10. So over 0.01. And our solubility in HCl will now be 1.8 by 10 to the power negative 8. So now what is our conclusion? In water, the solubility was this, but in HCl, it was this. So 1.34 by 10 to the power minus 5. 1.8 by 10 to the power minus 8. Which one is bigger? This is bigger, right? Yeah, when you're comparing negative exponents of 10 and you check if the exponents are different, the bigger one is the one with the less negative exponents. The smaller one is the one with the more negative exponents. But if the exponents were equal, then you ignore the exponents and come and check the actual numbers itself. You see, so we've done this. So if they're equal, then this, if the exponents are equal, then the one who will be bigger will be this, because this actual number is bigger than this. Back to the question. So we can see perfectly that in HCl the solubility has decreased. So our conclusion is that what? Common ion effect reduces our solubility. Common ion effect decreases what? Solubility. So as I initially said that this works on Le Chatelier's principle. Le Chatelier's principle. This is what we have. By HCl, the concentration of what? Cl minus was increased, extra was added, which means that if you increase this concentration, the equilibrium position will shift backward to decrease this concentration again. So if a system is under equilibrium and then you increase something or decrease something, the equilibrium position will shift in a direction that will reduce it again, like that will bring it back to normal. So when you increase it, the equilibrium position will shift backward so that it will decrease it again. So in shifting backward, we are now going back to form the salt. Instead of the salt dissociating, we are now going back to form the salt. So we are reducing the solubility. Okay, let's wrap up. Solve questions here. Oh yeah, this is my favorite question. This is a question on fractional precipitation. You know what? Let's make this our last question. This particular one is very, very high yield as well. So we have three questions to go. Oh yeah, I like these questions too. If I was a lecturer, I would have brought these guys. So let's see. One form of kidney stones is calcium phosphate, which has a KSP of this. Okay, an example of urine contains this concentration of calcium ions and this concentration of PO4 phosphate ions. Calculate the ionic product or reaction quotient and predict whether the calcium phosphate will precipitate or not. Okay, so this is what we have to do. Reaction quotient or ionic product is the same expression as KSP, but we are using the actual concentration of what the ions given. So let's see. Calcium phosphate aqueous Ca2 plus send this there aqueous plus PO4 3 minus aqueous. You have to balance the equation, isn't it? You need three atoms of calcium, and all this as a unit should be twice. Okay, yeah, we are not using the solubility itself to calculate the concentration. This is ionic product, not KSP. KSP use solubility, but ionic product, we are going to use what? The actual concentrations of the ions. But just that the expression is the same. The expression is the same. So to the power 3 to the power 2. Calcium ion concentration we're given. So this one is just straightforward, isn't it? And this one too was given. We are going to get 1.0 by 10 to the power minus 25. These are any products. Now we said we should predict whether precipitate will be formed or not. So this is a concept. If your ionic product is less than the KSP, you have an unsaturated solution. If your ionic product is equal to KSP, you have a saturated solution but no precipitate. If your ionic product is greater than your KSP, you still have a saturated solution, but then with what? Precipitate. So let's check. Ionic product. Where is the KSP? KSP is here. We are comparing this to this. We can see that ionic product is greater than what? KSP. So precipitate will form. That's it. Next question. Exactly 0.400 liters or 0.500 molar lead 2 and 1.60 liters of 2.50 by 10 to the power minus 2 molar Cl minus are mixed. They are mixed together. Form a solution. Calculate the ionic product. Predict whether lead 2 chloride will precipitate or not. This is the KSP of lead 2 chloride. So now that we've mixed them, they give us concentration and volume. So let's find their initial moles. So initial moles of PB2 plus. Oh, sorry, not concentration. So initial mole is CV. So we just multiply 0.500 by 0.4. This is going to give us 0.2 mole. Then we can go ahead and get what? The initial mole of what? The Cl minus. To be also CV, concentration by volume. So here too we are going to get 0.04 mole. These are the initial moles. After we mix them, the total volume was now what? 0.400 plus 1.60. So our total volume is now 2.0 liters. So now that I have a new total volume, you are going to get what? New concentrations. Good. So let's get our new concentrations. So the new concentrations here. So the concentration of the Pb2 plus will be the moles over the total volume. So we already know the moles 0.2. Total volume is 2.0, isn't it? So you are going to get what? 0.1 molar. Concentration of Cl minus now. Mole over total volume. The moles was 0.04. Total volume is 2.0. We are getting 0.02 molar. Now we know the concentrations of the ions and we know the Ksp. So let's write our equation of dissociation of the salt. Pb2 plus Cl minus aqueous we balance 2. Ionic product is concentration of Pb2 plus multiplying concentration of Cl minus to their exponents. This one 1, this one 2. We know the concentration of this in the mixture over here. So 0.1 over here to 0.02 squared. So you're going to get 4.0 by 10 to the power minus 5. Now we can compare it to what? Our KSP. When you compare, we realize that you see the exponents are the same, minus 5, minus 5. So you compare the actual numbers, 4 and 1.6. So obviously, 4 is greater than 1.6. So since ionic product is greater than KSP, yeah, lead 2 chloride will precipitate. Yeah, okay. My favorite question is here. Okay. Solid sodium chloride is really added to this concentration of each of these ions. Okay. Which compound precipitates first? So it's in three parts. This is the first part. Okay. We're given the KSPs of what? The compound. This is fractional precipitation. So what you have to do here is that you have to you can just get it without even calculating. The one with the least KSP will have the least solubility. So that's it. If you compare all this, the one with the least KSP here is silver, gold, 1 chloride. So this will precipitate first, but you can calculate it. So the next question says calculate the concentration of Cl minus required to initiate the precipitation of each of the ion. So now, if you take CuCl aqueous, we are going to get what? Cu plus aqueous plus Cl minus aqueous, isn't it? Then our KSP is going to be concentration of Cu plus multiplying concentration of Cl minus. So we can get the concentration of Cl minus required to be KSP over concentration of Cu plus. And over here we know our KSP for copper, 1 chloride 1.9 by 10 to the power minus 7. So over the concentration of copper, each of them are 0.010. So we can get this concentration over here 1.9 by 10 to the power minus 5. So we are going to do same for this guy for all of them. So for the silver, 1 chloride our concentration of Cl minus, if you write the expression, it will still be KSP over concentration of silver ions. They all have the same concentration. We are going to get 1.8 by 10 to the power minus 8 molar. And for the last one, the gold, can get the concentration of the Cl minus to still be the Ksp for the gold 1 chloride over concentration of the gold 0.010. Here too, we are going to get 2.0 by 10 to the power minus 11 molar. So the one that requires the least amount of chloride ions will precipitate first. Compare this to that. Look at the negative power. So this one requires the least amount of Cl minus. So this will precipitate first. I told you you can just know it by watching the Ksp value. The one with the least Ksp will precipitate first. So this is how you solve this one. Now calculate the percentage of Au plus ions that will precipitate before AgCl begins to precipitate. So before AgCl begins to precipitate, which means that at the time that AgCl was precipitating, there was still some amount of gold in there. So at that time, what concentration of Cl minus do you require to precipitate the Ag, the silver? You require this concentration, which means that if you use this concentration, with this concentration, check the equilibrium equation for the Au for the gold 1 chloride and then get the concentration of gold Au plus from there. So from this equation, Ksp is equal to Au plus Cl minus. So you can get what concentration of Au that we need at that time, Ksp over concentration of Cl minus if we use the concentration of what Cl that we need to precipitate our silver. So the Ksp was 2.0 by 10 to the power minus 13 over concentration of Cl needed to precipitate silver. So from here we can get 1.11 by 10 to the power minus 5. Let me say 1.1. So we've gotten the concentration of gold that was remaining. So since we know the gold remaining and we know the initial amount of gold was this, we can get the gold that precipitated. So concentration of Au that precipitated is equal to the initial, which was 0.010 minus the amount remaining, so 1.1 by 10 to the power minus 5. So the one that precipitated is 9.989 by 10 to the power minus 3. And we can find the percentage of Au plus that precipitated to be 9.989 by 10 to the power minus 3 over 0.010 by 100%. Then we get 99.8